Somewhere out there, a single photograph reminded us how small we really are. It didn't show a planet. It showed perspective. In 1990, Voyager 1 turned its camera back toward Earth from nearly 4 billion miles away. What it captured was a pale blue dot, barely visible, suspended in a beam of sunlight. Carl Sagan called it home. Everyone we've ever known, he said, lived their entire lives on that speck of dust. But here's what no one talks about. That photograph also captured something else. A silence. The kind that sits behind the stars and between galaxies. The kind that asks a question so old, so persistent, that every civilization has tried to answer it. Where did all of this come from? We've been told the answer. 13.8 billion years ago, the universe exploded into existence. The Big Bang. A moment of creation so violent, so total, that space and time themselves were born from it. But that's not the whole story. Because if everything started then, if the universe truly began in that singular moment, what was there before? And what does before even mean if time itself didn't exist yet? This is the question that breaks physics, the question that separates what we know from what we can only imagine, the question that might not even have an answer. What came before the Big Bang? Let's start with what we think we know. The Big Bang isn't an explosion in space. It's an explosion of space. Imagine the universe as a balloon and every galaxy as a dot on its surface. As the balloon inflates, the dots move apart, not because they're traveling through the rubber, but because the rubber itself is stretching. That's what's happening to our universe. Space is expanding. Galaxies are moving away from each other, and the farther away they are, the faster they recede. We know this because of a man named Edwin Hubble, who in 1929 discovered that light from distant galaxies was stretched, redshifted, like the pitch of an ambulance siren dropping as it drives away. If the universe is expanding now, then it must have been smaller in the past. Rewind far enough, and everything, every star, every planet, every atom, collapses into a single point, a singularity, infinitely dense, infinitely hot, the beginning. Or so the story goes. But there's a problem. Actually, there are many problems. For one, singularities don't really exist, at least not in the way we think. They're mathematical artifacts, places where our equations break down, where numbers spiral toward infinity and stop making sense. General relativity, Einstein's masterpiece, predicts a singularity at the start of the universe. But general relativity also stops working there. It's like a map that guides you to the edge of a cliff, and then simply ends. Quantum mechanics doesn't help either. At the scale of the singularity, smaller than an atom, smaller than anything we've ever measured, quantum effects dominate. Particles flicker in and out of existence. Cause and effect blur. But quantum mechanics and general relativity don't speak the same language. They describe the universe in fundamentally incompatible ways. One deals with the very large, the other with the very small. And at the moment of the Big Bang, the universe was both. So here's the uncomfortable truth. We don't actually know what happened at the beginning. The Big Bang explains the evolution of the universe after that first moment, but it tells us nothing about the moment itself. It's a story with a missing first page, and that missing page might be the most important one. There's a deeper issue, though, one that's harder to see but impossible to ignore once you notice it. The singularity isn't just a place where physics breaks down. It's a place where time breaks down. Think about what time actually is, not the clock on your wall or the calendar on your phone, but the thing itself, the dimension that lets change happen. In our everyday experience, time flows. The past is behind us, the future ahead. Cause precedes effect. We remember yesterday, but not tomorrow. But according to general relativity, time is woven into the fabric of space. They're not separate entities, There's space-time, a single four-dimensional structure that bends and warps in the presence of mass and energy. When space expands, time stretches with it. When space contracts, time compresses. At the singularity, space shrinks to zero. And if space is zero, then time is what exactly? This is where language fails us. We want to ask, what happened before the Big Bang? But before is a word that only makes sense if time already exists. It's like asking what's north of the North Pole. The question contains its own impossibility. St. Augustine understood this in the 4th century. When asked what God was doing before he created the universe, Augustine replied, "Time itself was created with the universe. There was no before." He was joking, but he was also right. If the Big Bang created time, then asking what came before, it is like asking what caused cause itself. It's a recursive loop that folds back on itself, leaving us stranded at the edge of comprehension. But humans are stubborn. We don't accept edges. We build bridges. The bridge begins with quantum mechanics. In the classical picture of the Big Bang, the singularity is a point, precise, definite, unavoidable. But quantum mechanics doesn't deal in certainties. It deals in probabilities. At quantum scales, particles don't have exact positions or velocities. They exist in a haze of possibilities, collapsing into definite states only when observed. What if the same is true for the universe itself? In the 1960s, physicists began applying quantum mechanics to the very early universe. What they found was strange and beautiful. Near the Planck scale, the smallest possible unit of space and time, reality becomes probabilistic. The universe doesn't have a single definite history. It has many histories, overlapping, interfering, splitting and merging like waves on water. At this scale, the singularity might not be a point at all. It might be a smear, a quantum blur where space-time itself fluctuates wildly, where the distinction between existing and not existing becomes meaningless. This is the realm of quantum cosmology, and it's where some of the strangest ideas in physics begin to emerge. One of those ideas is the Hartley-Hawking state. Proposed by James Hartley and Stephen Hawking in 1983, it suggests that the universe has no boundary in time, not because it goes on forever, but because at the Big Bang, time behaves differently. Instead of a beginning, there's a smooth, continuous surface, like the surface of a sphere. Just as the Earth has no edge, the universe has no starting point. In this model, asking what came before the Big Bang is like asking what's south of the South Pole. The question assumes a direction that doesn't exist. Time, near the Big Bang, curves back on itself. It becomes space-like. The beginning isn't a moment in time. It's a region of space-time, finite but unbounded. It's elegant, it's mathematically consistent, and it completely redefines what we mean by beginning. But it's not the only idea. There's another possibility, one that's older, stranger, and in some ways more intuitive. What if the universe didn't begin at all? What if the Big Bang wasn't the start of everything, but just a transition? A moment when one phase of the universe ended and another began. This is the idea behind cyclic cosmology, and it's been around, in one form or another, for thousands of years. Ancient Hindu texts describe a universe that expands and contracts in endless cycles, each lasting trillions of years. The Greek philosopher Empedocles imagined the cosmos alternating between unity and separation, creation and destruction, forever. Even Friedrich Nietzsche proposed the concept of eternal return, the idea that the universe repeats itself infinitely, with every event occurring again and again across endless time. Modern physics has revived these ideas, but with mathematical precision. In the 1920s, a Russian physicist named Alexander Friedmann discovered that Einstein's equations allowed for a universe that could expand and then contract, a big crunch following the Big Bang. If the universe contained enough matter, gravity would eventually overcome expansion, pulling everything back together until it collapsed into a singularity. And maybe, just maybe, that singularity wouldn't be an end. Maybe it would bounce. The problem is that Einstein's equations don't allow for a bounce. At the singularity, general relativity breaks down. The universe would contract to infinite density, and that's where the math stops working. There's no way, within classical physics, to continue past that point. But quantum mechanics changes things. In the 1980s, physicists began exploring quantum cosmology models that replaced the singularity with a bounce. Instead of contracting to a point, the universe would reach a minimum size, still incredibly small, but not zero, and then rebound. The Big Bang in this picture is really a big bounce. And before our universe, there was another one. And before that, another. An infinite chain of cycles, each ending in a crunch and beginning with a bang. It's a compelling idea, but it faces challenges. For one, what happens to information across cycles? If the universe collapses and then re-expands, does anything from the previous cycle survive? Or is each cycle a fresh start, with no memory of what came before? And then there's entropy, the tendency of systems to move toward disorder. Each cycle would presumably increase the universe's entropy. Over infinite cycles, entropy should be infinite. But our universe has relatively low entropy. It's ordered, structured, full of galaxies and stars and life. How did it get that way? Some models propose a mechanism to reset entropy at each bounce. Others suggest that cycles aren't identical. Each one is slightly different, evolving over time. But these are patches, not solutions. The cyclic universe remains elegant in concept, but troubled in detail. Still, it offers something the standard Big Bang doesn't. Continuity. A universe without a true beginning. A cosmos that has always existed, in one form or another, unfolding across eternity. But there's a different kind of eternity, one that doesn't involve cycles at all. Imagine a universe that begins not from a singularity, but from nothing. Literally nothing. Not empty space, but the absence of space. No time, no energy, no matter, just nothing. How do you get something from nothing? Quantum mechanics has an answer, and it's unsettling. In the quantum world, nothing is unstable. Even in a perfect vacuum, empty space with no particles, no fields, no anything, quantum fluctuations occur. Virtual particles pop into existence in pairs, exist for a fraction of a second, and then annihilate. This isn't speculation. It's been measured. The Casimir effect, first observed in 1948, proves that empty space seethes with these fluctuations. Now take that idea and scale it up. What if the entire universe is a quantum fluctuation? This is the premise of the quantum creation model, first proposed by physicist Edward Tryon in 1973. He suggested that the universe is a vacuum fluctuation, an accident essentially. A random blip in the quantum foam that instead of collapsing back into nothingness, inflated into a universe. It sounds absurd, but the math works. The key is energy. In general relativity, gravitational energy is negative. The energy stored in matter and radiation is positive. If you add them up for the entire universe, they might cancel out. The total energy of the universe could be zero. If that's true, then the universe isn't violating any conservation laws. It's not creating energy from nothing. It's just rearranging zero into two opposite forms, positive and negative. Matter and gravity, something and its shadow. From nothing, you can get a universe if the universe's total energy is zero. It's a strange thought. Stranger still when you realize what it implies. If the universe can arise from a quantum fluctuation, then it didn't need a cause. It didn't need a creator. It didn't need anything before it. It just happened. Spontaneously, uncaused. Philosophers have wrestled with this for centuries. Gottfried Leibniz in the 17th century asked, "Why is there something rather than nothing?" He believed there had to be a reason, a necessary being that explained existence itself. But quantum mechanics suggests otherwise. Maybe there is no reason. Maybe the universe exists because it can. Because quantum mechanics allows it. Because nothing is unstable and something is possible. It's not a satisfying answer, emotionally, but it's consistent with what we know about how reality works at the smallest scales. And it's not the only way to think about quantum creation. There's a variant of this idea that's even stranger, and it involves inflation. Inflation is one of the most successful theories in modern cosmology. Proposed by Alan Guth in 1980, it suggests that in the first fraction of a second after the Big Bang, the universe expanded exponentially, doubling in size every tiny instant. This rapid expansion smoothed out irregularities and stretched quantum fluctuations to cosmic scales, seeding the galaxies we see today. Inflation explains a lot. It explains why the universe is so uniform. It explains why space is flat. It explains the pattern of fluctuations in the cosmic microwave background, the afterglow of the Big Bang. But here's the twist. Once inflation starts, it might never fully stop. In many models, inflation doesn't end everywhere at once. It stops in some regions, creating pocket universes like ours. But in other regions, it continues. And those inflating regions spawn more pocket universes, which spawn more inflating regions, which spawn more pocket universes. Forever. This is eternal inflation, and it paints a picture of reality far stranger than anything we've imagined. In this view, our universe, the observable cosmos with its 100 billion galaxies, is just one bubble in an infinite foam. Each bubble has its own Big Bang, its own laws of physics, its own history. Some bubbles might have different constants of nature. Some might be lifeless. Some might be unimaginably vast or unimaginably small. And the foam itself has no beginning. Inflation has always been happening, somewhere. Pocket universes are always forming. The multiverse, if we can call it that, is eternal to the future, and possibly eternal to the past. There's no before the Big Bang, because the Big Bang is just the start of our bubble. The larger structure, the inflating multiverse, has always existed. It's a dizzying idea, and it raises as many questions as it answers. If eternal inflation is true, then our universe isn't special. It's one outcome among infinite outcomes. The constants of nature that allow stars and planets and life, those might just be accidents, random draws in a cosmic lottery. We exist not because the universe was designed for us, but because in an infinite multiverse, every possibility happens somewhere. It's humbling, and for some, troubling. But it also offers a kind of answer to the question of origins. Not a beginning, but an eternal process. Not a creation, but a structure that has always been unfolding. Still, there's a problem with all of these models. They assume space and time as we understand them. They assume quantum mechanics as we know it. They assume general relativity as Einstein formulated it. But what if those assumptions are wrong? What if space and time aren't fundamental? What if they emerge from something deeper? This is the promise of string theory, and it takes us into territory that's almost impossible to visualize. String theory proposes that the fundamental building blocks of reality aren't particles. They're tiny, vibrating strings of energy. Different vibrations produce different particles. Electrons, quarks, photons. Everything in the universe in this view is the music of strings. But here's the catch. For string theory to work mathematically, space needs more than 3 dimensions. It needs 10, or 11, depending on the version. Where are these extra dimensions? They're hidden, curled up at scales so small we can't detect them. Imagine a garden hose. From far away, it looks one-dimensional, just a line. But up close, there's another dimension. the circular dimension around the hose. String theory suggests that every point in space has extra dimensions like that, coiled up too tightly to see. And in this higher dimensional space, the Big Bang might not be a singularity at all. One version of string cosmology, called the ekpyrotic model, proposes that our universe is a three-dimensional brane, short for membrane, floating in a higher dimensional space. The Big Bang occurred when our brain collided with another brain. The impact released enormous energy, creating the hot, dense state we call the early universe. In this picture, the Big Bang isn't a beginning, it's a collision. And before the collision, both brains existed. Time existed. Space existed. The ekpyrotic model solves some problems. It avoids the singularity. It explains why the universe is so uniform. And it suggests a mechanism for cyclic cosmology. The brains could collide again and again, producing a series of Big Bangs over endless time. But it introduces new questions. What are the brains made of? What determines when they collide? And most fundamentally, where did the higher dimensional space come from? String theory doesn't answer that. It pushes the question back a layer, but it doesn't resolve it. And that might be the deepest lesson here. Every answer we find leads to a deeper question. There's one more idea worth considering. It's not a theory, exactly, more of a principle. It's called the cosmological no-boundary proposal, and it was developed by Stephen Hawking and James Hartle. We touched on it earlier, but it's worth exploring more deeply. The proposal starts with a simple question. What does it mean for the universe to have a boundary in time? In classical physics, a boundary is an edge, a place where something stops. But in quantum cosmology, boundaries behave differently. Hawking and Hartle suggested that instead of thinking about the universe's history as a timeline, a sequence of moments stretching back to a beginning, we should think about it as a geometry, a shape in four-dimensional space-time. Near the Big Bang, they proposed, time behaves like space. It doesn't have a sharp starting point. Instead, it curves smoothly, like the surface of a sphere. If you trace backward in time, you don't hit a singularity. You simply loop around, like traveling south on Earth. There's no edge to reach. In this model, the universe is finite in time, but has no boundary. It exists as a complete, self-contained structure. The question, what came before, doesn't arise, not because the answer is forbidden, but because the question doesn't apply to the geometry itself. It's a beautiful idea, and it's deeply strange. One consequence is that the universe, in this view, is its own explanation. It doesn't require a cause, because causality only makes sense within time, and time is part of the structure itself. The universe isn't caused by something outside it. It simply is. This raises profound philosophical questions. For centuries, theologians and philosophers have argued that the universe must have a first cause, something or someone that set everything in motion. But the no-boundary proposal suggests otherwise. It suggests that the universe can be self-contained, requiring nothing external to explain its existence. Some see this as liberating, others find it unsettling. But science isn't in the business of comforting us. It's in the business of describing reality as accurately as possible. And if reality doesn't conform to our intuitions, if it doesn't require a beginning or a cause, then that's simply what we have to grapple with. So, where does this leave us? We've explored cyclic universes that bounce forever, quantum fluctuations that produce something from nothing, eternal inflation that generates infinite bubbles, higher dimensional brains colliding in unseen space, geometries where time curves back on itself, erasing the very concept of a beginning. None of these ideas are proven, none are certain, but all of them are serious scientific proposals grounded in mathematics and consistent, at least partially, with what we observe. And yet none of them fully answer the question, what came before the Big Bang? Maybe that's because the question itself is flawed. Maybe before doesn't apply. Maybe the universe didn't begin in the way we think about beginnings, a moment when something starts. Maybe it has always existed in some form or another, woven into a structure where time and space are just features of a deeper reality. Or maybe the answer is beyond our reach, not because we're not smart enough, but because the tools we have, our equations, our experiments, our ways of thinking, are fundamentally limited. We're like fish trying to understand the ocean by studying water. We're immersed in the thing we're trying to explain, and that might make certain truths inaccessible. There's a humility in that thought. A recognition that the universe might be stranger than we can imagine, that our place in it is smaller and more contingent than we'd like to believe. But there's also something profound in the fact that we're asking these questions at all. Here's what strikes me most about this entire inquiry. We're a species that evolved on a small planet orbiting an ordinary star in an unremarkable galaxy. Our ancestors survived by understanding the patterns of weather, the behavior of animals, the growth of crops. Evolution didn't design our brains to comprehend the origin of space-time or the nature of quantum fluctuations. And yet, we do. Imperfectly, incompletely, but we do. We've built telescopes that can see light from galaxies formed just after the Big Bang. We've written equations that describe the behavior of matter at temperatures 1 billion degrees hot. We've measured the faint ripples in space-time left over from the universe's infancy, and we've used those ripples to reconstruct what happened in the first fraction of a second. It's astonishing, really, that a collection of atoms, organized into neurons, firing electrical signals across synapses, can look back across 13 billion years and ask, how did this begin? And maybe that's the real answer to the question of origins. Not a theory or a model, but a recognition. The universe is the kind of place where matter can become conscious, where structure can emerge from chaos, where questioning is possible. We might never know what came before the Big Bang. We might never find a final theory that explains everything. But the fact that we're here, asking the question, is itself part of the story. 13.8 billion years ago, something happened. Whether it was a beginning or a transition or a quantum fluctuation or a collision of brains, we don't fully know. But it set in motion a chain of events that led to stars and planets and chemistry and biology and eventually, impossibly, to you and me. We're made of recycled stardust, carbon forged in the cores of dying suns, oxygen created in supernova explosions. Every atom in your body is older than the Earth itself, and it's been part of countless other structures before it became you. In a very real sense, we're not separate from the universe. We're a way the universe looks at itself, a way it tries to understand itself. And if the universe had no beginning, if it's always existed in some form, then we're part of something eternal, something that has always been unfolding, always evolving, always reaching toward complexity and awareness. There's a comfort in that, not the comfort of certainty, but the comfort of continuity, a sense that we're part of a story that's larger than ourselves, older than memory, deeper than time. I think about the Voyager photograph again, that pale blue dot, suspended in a sunbeam. From that distance, Earth is barely visible. All of human history, every war, every love story, every scientific discovery, happened on a pixel. And beyond that pixel, there are trillions of galaxies, each with billions of stars, stretching across distances so vast that light takes billions of years to traverse them. It's easy to feel insignificant in the face of that scale. Easy to feel like nothing we do matters. But maybe the opposite is true. Maybe the fact that we exist at all, that we can think and wonder and ask questions about the origin of everything, is the most significant thing in the universe. Maybe consciousness is rare. Maybe it's precious. Maybe we're one of the ways the cosmos has learned to reflect on itself. And if that's true, then our quest to understand where we came from isn't just an intellectual exercise. It's a fundamental part of what the universe is doing. It's the cosmos waking up to its own existence. The question of what came before the Big Bang might never have a final answer. The universe might be too strange, too vast, too fundamentally weird for our minds to fully grasp. But that doesn't mean we stop asking. Because in the asking, in the wondering, the exploring, the reaching toward understanding, we're participating in something extraordinary. We're part of the universe's attempt to know itself, and maybe that's enough. Maybe that's everything.